Yeah, welcome back, everybody. Let's go ahead and dive right back in. We left off in the last video talking about how we could solve the closest point problem as a minimization problem. So specifically, we had this theorem, all right? This theorem telling us that if we were working in an arbitrary inner product space, that we could translate this closest point problem there into a question in Rn with the standard Euclidean inner product, the standard Euclidean dot product. And this would allow us to invoke our minimization principle from before. So by choosing a basis, we can create coordinates so that we can describe this closest point problem in an arbitrary inner product space. And that is extraordinarily useful, especially if we're trying to put stuff into a computer where a computer has no idea what an abstract inner product space looks like and instead can only work with Euclidean inner product spaces. So we would like to kind of continue this and maybe think about different ways of framing the problem. See if there's another way that might be useful to us. And in this case, if we have a quick look at this example. So we are continuing from where we left off last time, and I would like to solve the closest point problem for this matrix whose columns are given by whose columns are given by these vectors that form a basis for this subspace W in the standard inner product space on R4, or standard R4 with the standard dot product. Now, we know that if we were to figure out or ask ourselves for some vector B to be in, wrong direction, right? If we're asking for some vector B to be in this subspace W, then we're really asking, is B in the image, question mark, is it in the image of this matrix A down here? And we solved this maybe not way back, but we did solve this completely back in chapter 4, saying that B is in the image of A if and only if B is perpendicular to the co-kernel of that matrix. So that's exactly what we're checking here. This is the Fredholm alternative making an appearance, and it allows us to see that, okay, yes, we have a collection of linearly independent dudes. That's why this is a positive definite Gram matrix. But if we're not careful about our choice of solution vector, we can show that this guy B, if I take the dot product here, this guy with a basis of W, which consists of a single vector, this will be 2 minus 1 minus 1 plus 1 for a total of 1. That's not 0. That means that B can't be in my subspace. Right, see how much quicker that is. We could also just go ahead and throw that into MATLAB, but I thought this was a good opportunity to show the Fredholm alternative and how it's still useful beyond chapter 4. Okay, so we definitely know that B is not in this subspace, but the question is, how close is it to being in that subspace? Well, we can go ahead and set up our problem. So we get our Gram matrix from before. This F vector, right? Remember, this is going to be all these vectors dotted against, all these basis vectors dotted against B. So in the first one, we'll see 2 plus 1 plus 1 plus 1, that'll give us the 5. Then 2 minus 1 plus 1 minus 1, that'll give us a 1. And then 2 plus 1 minus 1 minus 1 will give us the other 1. So that's my F vector. And then C is just going to be the length of this guy, or the square length of the B vector. So this will be 4 plus 1 plus 1 plus 1, and there's the 7. So sure, we can frame this as a we can frame the closest point problem as a minimization problem with these three components, these three elements that will make up our quadratic function that we need to minimize. Right, and we know that the solution for that, for the minimum distance, or the smallest distance that this guy, that B is away from that subspace, is given by these weights that are computed as K inverse times F. And K inverse, K luckily enough is just a diagonal matrix, so inverting him is just as simple as flipping over each of the elements along the diagonal. So there's 1/4 times the identity multiplied into this vector F, and that gives us the weights that we need to strap on to our basis in order to create the vector that is closest in W to the vector B. So if I use these weights, so these guys, oh, wrong color, these guys go as the weights sitting in front of each of the basis vectors from up here. So this was W1, W2, W3 from the notation before. And that means that I create this vector that belongs to the subspace W and creates a norm, or creates a distance of, and this is actually D squared technically. Yeah, is that right? Yeah, no, this, so I believe that should be a square. So that means that the actual distance is the square root of 1/2. So we can figure out how far away this vector is from belonging to that subspace, and we solve it as a closest point problem, which we've just seen in the previous video is another way of framing a minimization problem, or can be framed as a minimization problem. And just as a quick remark here, the way that we set this one up, specifically the way we set this up, is that K was a Gram matrix for a specific A, okay? And F was going to be the weights associated with each of those vectors, or effectively a projection of B onto these columns, or onto this set of weights, or set of basis vectors. So what we're really thinking about here is that this guy, this A transpose B, is a whole bunch of dot products thrown into one, and these are just how much of B lives in each of the basis vectors, which can actually be thought of as kind of a projection, right? So we want this solution to be thought of as K inverse, which can be completely expressed in terms of A and its transpose. But remember, A transpose A is a whole bunch of dot products. So we are just projecting the crud out of this problem. And the way that we can think about this vector of weights that gets assigned to our basis is that it is a projection of this B vector onto the columns of a matrix. So this is how we can think of this as a projector form of the minimizer, or that we think of this particular form of the minimizer as a projection. And what it does is it solves that particular equation, right? Just multiplying AX equals B by A transpose on the left on both sides. And this creates what are called the normal equations for this system. Right? You will see them as the normal equations. And this we will see once again when we talk about least squares solutions. These normal equations play a pivotal role in that scenario, or in that setting as well. Okay? Awesome. Let's see another example in this same vein, where we're projecting solutions onto a subspace of something bigger. And this actually comes, this example comes straight out of the problem set. So if you haven't started working on it by now, you're welcome. This example is what we're going to be looking at in that scenario. We are trying to show that this vector, this x vector on the continuous functions from minus pi to pi with the L2 norm, or the L2 inner product specifically, can be represented as a linear combination of sines and cosines of increasing frequency. Okay, so k here is an integer greater than 0. So positive integer is another way to say that. But what we're doing is we are projecting this b vector onto this subspace that's spanned by these different cosine and sine functions of different frequencies, of increasing frequencies specifically. And if we go through that problem set, you will find the Gram matrix for this guy with respect to this inner product space is a diagonal matrix, indicating that this BK set, this BK basis for W, is actually an orthogonal basis. Right? It's not orthonormal because I haven't unitized these guys, but I can create an orthogonal basis. This is an orthogonal basis for that set, right? Or for that subspace. And the same deal goes that I can go ahead and project. Each one of these guys will be X inner product with, I don't know, cosine of NX or a sine of NX, something. It's going to be how much of X lives, or how much of cosine of, how much of each of these functions in BK lives in X, or how much of these functions contribute to creating the function X. Okay, and then finally, of course, C is going to be the square length of this B vector. So we've computed this one before. We know that will be 2 pi cubed over 3. Right? This is because we're doing this on the interval from minus pi to pi. That's why the pi shows up. Okay, we're good so far, I think. So we have the same minimization principle set up. And once we have that set up, the weights that go and associate with our basis, these x star weights, these are going to be given as this multiplication k inverse, which again is easy to compute with a diagonal matrix. And we're going to multiply that into f. And it shows, because a lot of these entries in f up here are 0. In fact, you can show that the only entries that survive this are the weights that are associated with the sine functions up here. Right? It skips over the 1, it skips over the cosine, but then 2 pi is how much sine of x projects on, how much of sine of x lives in x. Interesting. Maybe not too surprising though. X is an odd function, so it would stand to reason, since we're doing this over a symmetric interval, or an interval that is symmetric over the origin or past 0, that we should expect to get rid of all of the even components, or there shouldn't be any even functions living inside of this odd function. But I digress. All the weights then, we can actually compute this. It's not terrible. It's not great, but it's not terrible. You will see that these weights are given exactly, or will exactly give the vector in W that is closest to X. Right? Or that X, this vector is it is the vector in W that is closest to the vector X. And in this case, right, this is exactly an orthogonal projection, right? This is an orthogonal basis, and we're projecting directly onto this space spanned by beta k. So X projects directly onto this set, and this is exactly the principle behind a Fourier series. So more generally, right, so skipping Fourier for a second, if I have an orthogonal basis, then x star being k inverse times f in our minimization problem produces exactly the projection formula, or the coordinates in orthogonal projection that we got from the beginning of chapter 4. So this leads us to the following theorem, that if I have a subspace of an inner product space that is finite dimensional, and I choose some vector b in the total inner product space, it doesn't even have to be in W, just like above, the point in W that is closest to B is it is precisely the orthogonal projection of that vector B onto the subspace W. Kind of nifty now that we can now effectively do calculus in an abstract inner product space without actually doing calculus. Right? We are substituting the derivative computations, looking for critical points via the derivative, for using orthogonality to produce objects of minimal size. So this is how we skirt around doing multivariable calculus by using linear algebra. Kind of nifty, huh? And the last thing we'll say for this video is more about this projection. Right, so recall that if I were to create a, if I were to try to kind of fill up an infinite dimensional vector space with a basis, much in the way that I'm trying to do here with my Fourier basis, right, it's this guy right here. It's the truncated Fourier basis. Right? So I'm trying to add more and more vectors in there so that I eventually get to a spanning set of C minus pi to pi. But we'll see why that doesn't quite work out in a moment. But the point is that I would like to figure out what is the distance, what is that minimum distance between fk tilde and f, right? So fk tilde being the projection of f onto this subspace beta k. Right, so in the context of the previous problem, I am projecting x onto beta k, and that produces a function f tilde k. Right, this is the orthogonal projection of the orthogonal projection of my function x onto the subspace W. And if I were to follow this to the letter, if I follow what this distance means, right, I'm going to try to minimize the square distance between these two functions. Well, okay, the norm of f is easy enough to compute, but the distance here, if we use the minimization principle, we know that that minimum distance is exactly the norm of f squared minus f dot the weights x star, which I can now write in terms of a partial sum. Right? It's how much I have to add on to each and every one of these guys, because I know that this projection in an orthogonal basis is going to get me this formula. It's my generalized Pythagorean theorem, right? And we did this in the homework, right? The generalized Pythagorean theorem does show up here. And specifically, we see that this square distance, the square norm here, is exactly the algebra behind the Pythagorean theorem for this triangle, where f is the hypotenuse of the triangle. We project f onto W to get that bottom leg, and what's left is this height. This is the distance, the vector that's going to measure the distance between these two functions, or between these two vectors more generally. So if I am careful and I can keep going here, the square distance then is going to be however big the square norm of x was minus however big this projection was. And going back to the previous page, we already got the weights. And if I'm in an orthogonal basis, I can just go ahead and square the weights and add them all together. Okay, or add them all together, and that'll get me exactly the Pythagorean theorem, and it'll get me some idea of how far apart these two functions are. And we can show that this sum, as k goes to infinity, actually approaches 2 pi cubed over 3. What? So in other words, the larger my basis set is, the more vectors I want to put into that beta k, the better my approximation is of that function x. And I'm using, if I go back a page, means I'm using sines and cosines to get me an approximation of a polynomial. Right? This is totally backwards from what we're used to, where we were in Calc 2, right, talking about Taylor series, where we're using polynomials to approximate arbitrary functions. It turns out that process can be extended to the other way around. It can be reversed, where I can use trig functions to approximate other functions. And this is the whole premise behind Fourier analysis. Right? So there is a slight problem here. Right? So we do get really close, but we get really close on the interval from minus pi to pi. The problem is sines and cosines are periodic functions. This polynomial is not, right? This x function is not. So actually what winds up happening is that the limit, right, the limiting function of these approximations is actually discontinuous, right? And that's because it needs to be periodic, because I'm using periodic functions as my approximators. So actually, instead of just getting y equals x for my approximation, I have to repeat that over and over and over along different intervals, right? Along 2 pi long intervals outside of minus pi to pi. So in fact, my limiting function is discontinuous, which means it doesn't live in here, right? The limit function does not live in C from minus pi to pi. So there's a bit of a problem that the function, usually what we want our limit functions to be in the space that our sequence is, or where the sequence comes from. And we've already seen this guy definitely converges on something, or it looks like he wants to converge on something, but that function is not in our space. And this is because our continuous functions with the L2 inner product is not actually a complete inner product space. Right, and this is in the sense that not all sequences where the elements eventually get close to each other, get arbitrarily close to each other. These guys don't necessarily have to have limits that live in this space. Right, so this is not a complete inner product space. If we wanted to complete this guy, if we wanted to put those limiting functions in there, we get a formal definition of the square integral functions. We get a formal definition of what it means to be an L2 function. Right? L standing for Lebesgue. And I'll write that down. So Lebesgue, he has an S because he's French, don't hold it against him. But Lebesgue is a big name in measure theory and analysis. Right? He helped lay a lot of the framework for advanced calculus. Right? But once we complete this inner product space, we have an example of something called a Hilbert space. Now, Hilbert spaces are complete inner product spaces. It means that every Cauchy sequence, right, where all the elements in a sequence eventually get arbitrarily close pairwise, that these sequences definitely have limits, and those limits still live in L2. Right. So if you're interested in pursuing this any further, this is actually a great jumping off point for modern physics and partial differential equations theory. This is actually one of the starting points for graduate analysis or graduate math. If you ever go into a master's or PhD program, you will have to take a whole sequence. Oh shoot, and I just erased that. You have to take a whole sequence in what they call analysis or applied analysis. And this is just a funny way, or a more general way of saying advanced calculus. Right? This is a broader sense of analysis than what we do in undergrad in Calc 1 or in real analysis. If you're a major, you'll be taking real analysis 1, possibly 2. It is a very rigorous subject, and it's not for the faint of heart, but well worth the time investment if you have the opportunity. So anybody interested should consider taking either should consider taking modern physics if they're not already doing so. You should take a class in partial differential equations because you will see Fourier series there, I guarantee you. Or you can take a class in real analysis to start going further into advanced calculus. Or you can take an independent study to blend these guys and maybe go a little bit further than what you do in undergrad analysis. Or even more so, you'll see these methods show up in quantum mechanics as well. Right? Hilbert spaces are the bread and butter of quantum mechanics. Your observables are linear operators on Hilbert spaces. So this is where I'm going to kill this video. Next time, I believe, if I cheat a little bit and see where we're going, yep, we're going to go off into the least squares problem next.